Um, Alexander Dutoit came along next, and basically Alfred Wegener was getting a lot of trouble and flack for the fact that the continents didn't really fit together like a puzzle. He said, yeah, it kind of looks like a puzzle, but I mean, it's not a perfect puzzle, and I think you're probably trying to make up that story. And Alexander Dutoit basically said, well, what do you expect? Since Pangaea broke apart, it's been 200 million years, we've had a lot of weathering and erosion, you wouldn't expect a perfect fit. He said, however, if you were to look where the continental shelves meet the continental shelves, he said, I think the fit of the continents will actually be better. And sure enough, they were. Now, the other thing that Alexander Dutoit also did was he said that when Pangaea first broke apart 200 million years ago, it broke into two pieces, one piece called Laurasia, and the other piece called Gondwanaland. Next came Arthur Holmes, and Arthur Holmes is probably one of the most important contributors to plate tectonics because he said, you know what, there is no such thing as drifting. He said, but the continents are moving, and I know what's taking place. Down in the upper mantle, there are these big currents called convection currents, and they form due to unequal heating in the mantle. And whatever way these convection currents go or move, they move the continents that sit above. And so basically the movement of these continents is completely driven by the direction in which the mantle convection is taking place. And so that was Arthur Holmes' contribution, a very, very important one. So now we have the mechanism for how continents move, which Alfred Wegener didn't have. As you can see in this diagram, Holmes got a little diagram here from 1929. You can see a continent, and the coolest thing with this is that you can see that the convection currents are going this way and this way. So they're actually putting tension on that continental block, and they're going to rip it apart, just like two people, or one person, sorry, with a hand on each side of a big Turk bar, pulling it with tension in opposite directions. It's going to completely pull apart. So this kind of just shows you the influence that convection currents can have on continents. Later came along Hess and Dietz, and Hess and Dietz basically came up with their own theory or idea called the theory of seafloor spreading. And they basically noticed that some ocean floors were getting bigger. So one example would be the Indian Ocean, the Atlantic Ocean, and even the Red Sea. And what they figured is that in the middle of these oceans, there has to be a process taking place called seafloor spreading. That's basically making the oceans get bigger. Now, looking ahead, we know that seafloor spreading is real. It is occurring at mid-ocean ridges at divergent plate boundaries. At the time, Hess and Dietz didn't know that it was a plate boundary or anything like that. They just knew that there was probably lava pouring out in the middle of these oceans that basically was creating new rock. And knowing that Arthur Holmes had already discovered convection currents was kind of pushing it apart and making the oceans bigger. We now know that seafloor spreading occurs at about a rate of 2 centimeters per year. So when you combine the work of Arthur Holmes and Hess and Dietz, we're starting to really build closer to this whole idea of plate tectonics and what's actually taken place. Next up was J. Tuzo Wilson. J. Tuzo Wilson, I want to point out, is Canadian, but J. Tuzo Wilson was absolutely instrumental in the theory of plate tectonics. He is the guy who mapped where all the earthquakes and all the volcanoes were on our planet, connected the dots, and basically said, holy cow, the Earth is covered in plates, and we have 21 plates. In some places where land meets water is a plate boundary, like, for example, Vancouver. Vancouver is a place where North America hits the Pacific Ocean and is also a plate boundary. He also noted, though, that sometimes where land meets water is not a plate boundary. So, for example, in St. John's, Newfoundland, and if you're stood on Signal Hill, you're looking out into the Atlantic Ocean, that is not a plate boundary. In fact, you would have to go all the way across the Atlantic to the middle before you would actually truly get to the edge of the North American plate. So that was a huge discovery. The other thing that J. Tuzo Wilson is known for is the places where volcanoes were happening in the middle of plates, and they were kind of strange places, and nobody could really figure it out. And so two examples would be Yellowstone National Park in the middle of North America and Hawaii in the middle of the Pacific Ocean. And basically, he is the guy who came up with intraplate volcanism caused by hotspot volcanoes, which are just random magma chambers that just decide to burn through the crust in certain areas. He also discovered the third type of plate boundary, which is a transformed plate boundary where two plates simply slide past each other due to shear forces. But we're not really ready for that yet because in this evolution of the theory, we haven't fully developed plate tectonics and plate boundaries. But as you can see, J. Tuzo Wilson is incredibly influential because he discovered plates. So now we have the theory of plate tectonics. We have these 21 big rigid slabs of lithosphere called tectonic plates, and they move around in really, really, really slow, continual motions depending on what the convection currents are doing. We're getting to a point now where we're starting to figure out that you could have two plates come towards each other, two plates move away from each other, two plates slide past each other, and essentially what we're talking about is the different types of plate boundaries.